On June 24, 2026, the ground outside Caracas split apart in under a minute. Two massive earthquakes hit back to back. A magnitude 7.2 followed less than 60 seconds later by a magnitude 7.5 main shock. Buildings collapsed, roads tore open, and while rescue teams were still racing to reach survivors, something else was happening 400 miles above their heads. A brand new NASA satellite was watching, and it did something no satellite had ever done before during a disaster this size. It mapped the exact moment the Earth moved. This is the story of NISAR, the satellite that just changed how we respond to earthquakes forever. Let's start with what actually happened on the ground. Northern Venezuela sits on top of one of the most dangerous tectonic boundaries on the planet. It is the line where the Caribbean plate grinds against the South American plate, a slow, silent collision that has been building pressure for decades. On the morning of June 24th, that pressure let go. First, a magnitude 7.2 earthquake. Then, before the ground had even stopped shaking, a magnitude 7.5 main shock ripped through the same region. To put those numbers in perspective, a magnitude 7.5 earthquake releases roughly 22 times more energy than a magnitude 6.5 quake. These were not minor tremors. These were two major, independently destructive earthquakes stacked on top of each other within the same minute, hitting a densely populated coastline that was in no way prepared for a 1-2 punch like that. Together, the two quakes caused immense destruction across northern Venezuela. Coastal cities like La Guaira and the capital, Caracas, took the worst of it. Buildings that had stood for generations came down in seconds. The death toll and damage were severe enough to make this one of the most devastating earthquakes anywhere in the world in 2026. But here's what makes this story different from every earthquake disaster before it. For the first time ever, a satellite mission called NISAR was in position, ready, and fast enough to map exactly how the ground moved, within hours of the disaster happening. Stick around, because what this satellite saw is about to explain something rescue teams on the ground could never have figured out on their own. To understand why this matters, you need to understand what NISAR actually is. NISAR stands for NASA ISRO Synthetic Aperture Radar. It is a joint mission between NASA and ISRO, the Indian Space Research Organization. Two space agencies from two different countries building one satellite together. Its job is enormous. NISAR is designed to scan almost the entire surface of planet Earth, including every square mile of land and every ice sheet, once every 12 days. Twice, actually, since it covers the same ground from two different angles in that window. It does this using a technology called synthetic aperture radar. Instead of taking a normal photograph, which needs sunlight and clear skies, radar sends its own signal down to the ground and measures what bounces back. That means it can see through clouds, through darkness, through smoke and dust, day or night, rain or shine. There is another detail that makes NISAR especially good at reading earthquakes specifically. It observes Earth's surface at an angle, roughly 40 degrees off straight down, rather than looking straight down like many other imaging satellites. That angled view lets it capture both horizontal and vertical ground movement in a single pass, instead of only being able to detect motion in one direction. Earthquakes rarely move the ground in just one simple direction. Depending on the type of fault involved, the ground can shift sideways, drop downward, push upward, or some combination of all three at once. An angled radar view captures that complexity far more completely than a straight overhead shot ever could. NISAR was built to track a huge range of things: melting ice sheets, shifting farmland, groundwater changes, forest loss. But one of its most important jobs, maybe its most important job, is tracking the slow, invisible movement of the ground around fault lines. The kind of movement that builds up for decades before it finally snaps into an earthquake. Before this satellite launched, scientists had to rely on a patchwork of older instruments, aircraft flights, and ground sensors to track this kind of activity. NISAR was designed to do it constantly, globally, and fast. And on June 24, 2026, FAST got tested for the first time in the most serious way possible. Stay with me, because this is where the satellite's real superpower comes in. NISAR has a special mode called the Urgent Response System, or UR for short. It exists for exactly one purpose. When a major disaster happens, this system can process and deliver ground displacement data within 12 to 24 hours. Think about what that actually means. Normally, satellite data takes time to process. Orbits need to be calculated precisely. Images need to be compared and cross-referenced. That can take days, sometimes longer. The Urgent Response System skips ahead of all of that. It uses predicted orbit information instead of waiting for the fully precise version, trading a small amount of accuracy for enormous speed. The maps come out fast, and then get quietly refined and corrected within a day or two once the more exact orbital data comes in. This is a deliberate trade-off, and it is the right one for a disaster. In the immediate aftermath of a major earthquake, rescue teams do not need perfect laboratory-grade precision. They need a good enough answer, fast enough to act on, while people are still trapped and the window for finding survivors is closing by the hour. This was the first time this rapid response system had ever been used to map a large earthquake. Not a test, not a simulation, a real, devastating, real-time disaster. Within a single day of the Venezuela earthquakes, NISAR delivered maps showing exactly how far the ground had shifted and in which direction across the entire earthquake zone. That kind of speed had never existed before for an event this size. Older satellite missions could eventually produce similar maps, but the process typically took much longer, often long enough that the most urgent phase of a rescue operation had already passed by the time the data was ready. NISAR compressed that timeline down to hours, and what those maps revealed was stunning. Picture the map itself for a second, because this part is genuinely beautiful in a strange way. NISAR compared images of the ground from before the earthquake, taken on June 13th and June 18th, against images taken right after, on June 25th and June 30th. Same ground, same satellite. Two completely different moments in time laid directly on top of each other. The differences showed up in color. Red areas marked ground that moved east and upward. Blue areas marked ground that moved west and downward. And white areas, running in a thin line straight through the middle of the image, marked almost no movement at all. That thin white line was not empty. That thin white line was the fault itself, right where it ruptured deep underground, near a town called Moron. Because this was what scientists call a strike-slip fault, most of the movement did not happen up and down. It happened sideways. Two enormous chunks of Earth's crust sliding horizontally past each other, one moving one direction, the other moving the opposite direction, right along that thin white seam. Seeing that kind of movement mapped out so clearly, so quickly, gave scientists something they almost never get during a disaster this severe: clarity, in near real time, about exactly what the ground had just done. For scientists working the response, this kind of map replaces guesswork with hard measurement. Before this technology existed, understanding exactly how a fault slipped underground could take weeks of painstaking analysis, piecing together scattered ground sensors, aftershock patterns, and satellite images captured well after the fact. NISAR compressed that entire process down to a single day, delivering a direct, color-coded picture of the fault's behavior, while the disaster response was still in its most urgent phase. Here's the moment where this story stops being just a cool satellite image and starts explaining an actual mystery. Why was the destruction in Caracas and La Guaira so much worse than expected? The answer was sitting right there in the radar data. This section of the plate boundary includes a network of fault systems, including the San Sebastian Fault, and possibly part of the nearby Bocono system. According to the geophysicist who provided the maps, these faults had been quietly building up strain for a long time before finally releasing it all at once. That single sentence explains a lot. This was not some random, unexpected weak point in the crust. This was pressure that had been accumulating for years, maybe decades, finally letting go in one violent, concentrated burst. The scientists studying the NISAR data used it to feed directly into something called a finite fault model. That is essentially a detailed map of exactly how the fault slipped underground, section by section, including the eastern part of the rupture where earlier models had struggled to get accurate detail. With better data, scientists could finally explain why some neighborhoods were flattened while others nearby were barely touched. It came down to exactly where along that fault the slip was strongest and how that energy radiated outward toward the surface. This is not just interesting science trivia. This directly affects how emergency teams decide where to send help first, and how engineers assess which structures might be unsafe even if they look fine from the outside. There is also a longer-term benefit hiding inside this data. Every fault system that gets mapped this precisely after an earthquake becomes a better understood fault system going forward. Scientists can compare this event against decades of prior strain measurements along the same Caribbean-South American plate boundary, refining exactly how much pressure builds up here and roughly how often it tends to release. None of that lets anyone predict the next earthquake's exact date. Earthquake prediction, in that precise sense, still does not exist and may never exist. But it does let scientists refine hazard maps, which directly shape building codes, insurance models, and emergency planning for millions of people living along this same fault system for generations to come. Stick with me, because the story gets even bigger than just this one earthquake. This was NISAR's first real disaster test, but it was not the satellite's first appearance in earthquake science. Months before the Venezuela quakes, NASA ran a careful calibration campaign to make sure this satellite's radar would actually be trustworthy when a real emergency hit. In late April 2026, a NASA aircraft called the C-20A flew a series of missions over Central California, carrying an instrument called UAV-SAR. Its job was to fly directly over the San Andreas Fault, one of the most closely studied fault systems on the planet, and compare its own radar measurements against what NISAR was capturing from orbit. These flights served two purposes. They helped refine earthquake models for the San Andreas region specifically, and they validated NISAR's radar instrument, making sure the numbers coming down from space actually matched reality on the ground. The San Andreas Fault was a smart choice for this calibration work. It is one of the most heavily instrumented, most extensively studied fault systems anywhere on the planet, monitored for decades by ground sensors, GPS stations, and repeated aircraft surveys. If NISAR's radar measurements matched what scientists already knew about the San Andreas down to fine detail, that gave the whole mission team confidence the same technology would hold up anywhere else on Earth, including a fault system in Venezuela that had never been studied nearly as closely. The same UAV-SAR instrument carried aboard the C-20A also mapped land sinking in California's Central Valley, caused by groundwater being pumped out from underground. That is a completely different kind of ground movement than an earthquake, slow and gradual, instead of sudden and violent. But measuring it accurately requires the exact same underlying radar precision. By the time the Venezuela earthquake struck in June, NISAR was not an unproven experiment anymore. It was a calibrated, trusted instrument, ready to deliver real answers the moment a real crisis began. That kind of preparation is easy to overlook, but it is exactly why the response was so fast and so accurate when it actually mattered. Now, here's where this story connects to something even bigger than one satellite or one earthquake. NISAR is not the first time NASA has used satellites to study a major seismic event in near real time. Just weeks before the Venezuela earthquakes, another NASA French satellite called SWAT captured something equally remarkable: a massive magnitude 8.8 earthquake off Russia's Kamchatka Peninsula and the huge Pacific-wide tsunami that followed. SWAT gave scientists their first ever high-resolution, wide-area satellite view of a major tsunami actually crossing an entire ocean. It revealed the wave behavior was far messier and more scattered than existing models predicted, and it helped confirm the earthquake's rupture was even larger than initial estimates suggested. Before SWAT, scientists tracking a tsunami across the open ocean mostly relied on scattered buoys and tide gauges, essentially a handful of single points scattered across a vast ocean, trying to reconstruct the shape of an enormous wave from a tiny number of readings. SWAT changed that completely, capturing a continuous swath more than 100 kilometers wide, giving researchers something closer to a complete picture instead of a few disconnected dots. Two different satellites, two different disasters, same basic story. Modern Earth-observing technology is now fast enough and precise enough to watch these catastrophic events unfold in something close to real time, instead of piecing together what happened days or weeks later. That shift matters enormously for the people living through these disasters, because faster, clearer data means faster, smarter decisions about where help is needed most. Let's zoom out for a second and think about why any of this actually matters beyond the headlines. Earthquakes cannot be predicted. Not the exact moment, not the exact location, not with any technology that exists today. That has not changed, and NISAR does not change it either. What has changed is what happens in the hours and days right after a major quake strikes. Before satellites like NISAR, emergency teams often had to rely on eyewitness reports, damaged infrastructure, and slow, incomplete surveys to figure out where the worst destruction actually happened. Now, within a single day, scientists can hand emergency responders a precise map showing exactly how far the ground moved, in which direction, and where the fault itself ruptured. That data does not rebuild a single collapsed building, but it tells rescue teams exactly where to look first, and it tells engineers exactly which areas are most likely to still be structurally unstable. Think about what this means for a search and rescue commander standing in the middle of a disaster zone. Instead of splitting resources evenly across an entire city or relying on which neighborhoods happen to have the loudest news coverage, they can be handed a map showing precisely where the ground moved the most violently. That is where structural collapse is most likely to be severe. That is where survivors are most likely to be trapped. That is where limited rescue teams and equipment need to go first. The same logic applies after the immediate rescue phase ends. Engineers assessing which buildings are safe to re-enter and which ones need to be condemned can use the exact same ground displacement data to prioritize their inspections instead of working block by block with no guidance at all. Multiply that advantage across every major earthquake happening anywhere on the planet, and you start to see why scientists are calling NISAR a genuine turning point for disaster response, not just an incremental improvement. And this satellite is only getting started. It only recently finished its calibration phase before the Venezuela earthquakes put it to its first real test. Here's something worth sitting with for a moment. NISAR was not built specifically to respond to disasters. That is actually just one part of a much larger mission. The same satellite is constantly tracking melting ice sheets in Greenland and Antarctica. It is monitoring groundwater levels buried deep beneath farmland. It is tracking deforestation, crop health, and subtle shifts in land elevation caused by everything from mining to sinking coastlines. Every one of those missions relies on the exact same underlying capability, precisely measuring tiny changes in the position and shape of Earth's surface, over and over, every 12 days, for years on end. An ice sheet slowly thinning, a farm field slowly drying out, a coastline slowly sinking below sea level, a fault line slowly building toward its next rupture. All of it is the same fundamental measurement, just pointed at different problems. That is what makes NISAR so different from a typical disaster response tool built for one specific job. It was never designed only to watch for earthquakes. It was designed as a constant, planet-wide monitoring system, one that happens to be perfectly suited to react instantly the moment the ground moves somewhere unexpected. Earthquakes are just one chapter in a much bigger story this satellite is quietly writing about our entire planet, one radar scan at a time, every 12 days, over and over, for years to come. But when disaster strikes, all of that other data collection suddenly becomes secondary. The urgent response system kicks in, and NISAR's full attention shifts to the emergency in front of it. That is exactly what happened on June 24th. And it worked. So here is the bigger picture, the one worth remembering after this video ends. For most of human history, earthquakes have been almost purely reactive events. The ground shakes, buildings fall, and then people spend days or weeks trying to piece together exactly what happened and why. That timeline just got compressed into hours. A satellite in orbit read the exact motion of the Earth's crust after one of the most destructive earthquakes of the year, and handed that information to scientists and emergency responders before most rescue operations had even finished their first full day. We are entering an era where the planet itself is being watched closely enough and fast enough that the ground literally cannot move without us knowing about it almost immediately. Consider how different this would have looked even a decade ago. An earthquake this size, in this region, would have taken scientists weeks to fully map using older satellite technology, ground surveys, and slower processing pipelines. By the time a complete picture existed, the most critical window for saving lives would have already closed. NISAR did not just make that process faster, it fundamentally changed what is possible in the hours immediately following a catastrophe, when every single hour matters more than almost any other point in the entire disaster response timeline. That will never stop earthquakes from happening. Nothing can do that. The tectonic plates beneath Venezuela, beneath California, beneath dozens of dangerous fault systems around the world, will keep grinding against each other whether we are watching or not. But it might just save lives in the critical hours right after one does. And as more of these urgent response satellite maps get produced, faster and more accurately with each new event, that could end up being one of the most quietly important shifts in disaster science in years. If satellites reading the Earth's every move like this fascinates you, you need to see what happens when NASA's satellites caught a supermassive black hole getting flung out of its own galaxy at 1,000 kilometers per second. I made a full video on that. Watch it next. And if you want more stories like this one, where real NASA science reads the planet and the universe in ways that sound like science fiction but are completely real, hit subscribe, because this channel is just getting started.